Meeting many, we bundle count, before we add. And, flexible bundle numbers develops the child's innate mastery of many. A paradigm shift from line numbers, without units, to bundle numbers, with units. By Alan Tubb, at themathacademy.net, in Denmark. The goal of math education is that to master math, or to master many. All say, the goal is to master math, to later master many. But math is hard. Why not first master many, to later master math? So we ask, what math may grow from children's innate mastery of many, as developed before school? Grand theory questions, to mathematics education. Sociology asks, does mathematics education suffer from a goal displacement? What is its goal, to master many, or to master math? Philosophy asks, what to teach, existence or essence? And, is it ethical to teach students, if they already know? Psychology asks, how to teach. Guided interaction with existence, or mediated essence. Why teach children, if they already know? With education curing uneducatedness, we ask. To cure, be sure. The diagnosed, is not already cured. The diagnose, is not self-referring, teach mathematics, to learn mathematics. Core questions. What mastery of many, does the child have already? What could be a child-centered curriculum, in mastery of many? How do children master many? We ask a 3-year-old, how old next time? The answer is 4, showing 4 fingers. But, the child reacts strongly to 4 fingers held together, 2 by 2. That is not 4, that is 2 twos. Observation 1. Inside, children see what exists outside, bundles of twos, in space, and 2 of them, in time. So, children use, not line numbers, without units, but bundle numbers, with units. Observation 2, the child uses a full number language sentence, as in the word language, with a subject, a verb, and a predicate. That is 2 twos, shortened to the formula, T is 2 twos. Adults also use bundle counting with units, to master many, in time and space. Meeting many in time, repetition, and in space, extension, we ask. How many here, and how many in total, or simply, T is what? To bring many from time to space, we tally, stroke, 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 bundle, etc. And bundle count in polynomials. T equals 345. Equals 3 10 10, 4 10, 5. Equals 3 bundle bundle, 4 bundle, 5. Equals 3 times b squared, plus 4 times b, plus 5 times 1. So, digits are not numbers, but operators, needing digits, to become numbers. We ask, is this true always, or sometimes? 2 times 3 is 6. It is true always, since 2 times 3 is 2 threes, that can always be recounted as 6 ones. So it holds. 2 plus 3 is 5. Well, 2 weeks plus 3 weeks is 5 weeks, but 2 weeks plus 3 days is 17 days. It is true sometimes, since it is only valid with the same unit. So it may fold. And with fractions, 1 over 2, plus 2 over 3, is that 3 over 5, or is it 7 over 6? It depends on the unit. 1 of 2 apples, plus 2 of 3 apples, gives 3 of 5 apples, and not 7 of 6, as the school teaches. It is 7 over 6, only if taken of the same total. So, digits, and fractions, are not numbers, but operators needing numbers to become numbers. Inside and outside, the no-unit math greenhouse, the same question gives different answers. Inside the no-unit math greenhouse, 1 plus 2 is 3, always. This may be called mathema-tism, true inside, but seldom outside, the no-unit math greenhouse. Outside the no-unit math greenhouse, 1 plus 2 depends on the units. 1 meter plus 2 meter is 3 meter, but 1 kilometer plus 2 millimeter is still 1 kilometer, and 1 week plus 2 days is 9 days. A science must give valid statements, so mathematism is no science. So, we have 2 mathematics paradigms, one without units, and one with units. An inside no-unit math, number line, paradigm, where 1 plus 2 is 3, always, and an outside unit math, bundle number, paradigm, where 1 plus 2 depends on the units. The unit math paradigm builds on the philosophy, existentialism, where existence precedes essence. So, unit math describes real existence, and neglects institutionalized essence. Unit math is relevant for early childhood education, adult and migrant education, bringing back brains from special education. 1, 2, 3, etc., is a string of names, as is Monday, Tuesday, Wednesday, etc. With eyes closed, learning a string of number names by rote, is like learning other strings of names, for example, weekdays, months, etc. But, in a stack of 3 5s, the 5 bundle exists in space. And 3, the number of bundles, exists in time. So, we should include both the time number, and the space number, and the bundle unit, when counting existing things. 0 bundle 1, 0 bundle 2, etc. Teaching 1 plus 2 equals 3, without units, is falsified by 1 week plus 2 days equals 9 days. Addition is only meaningful with like units, according to the distributive law. T equals 0 bundle 1, plus 0 bundle 2, equals 0 bundle 3. Bundle counting becomes flexible, with overloads, and with underloads. Counting 10 fingers in 5s, we include the unit, to describe what exists. 0 bundle 1, 0 bundle 2, 0 bundle 3, 0 bundle 4, 0 bundle 5, 0 bundle 6, 0 bundle 7, 2 bundle less 2, 2 bundle less 1, 2 bundle 0. Here, we have an overload, when counting, 0 bundle 5, 0 bundle 6, 0 bundle 7, instead of 1 bundle 0, 1 bundle 1, 1 bundle 2. And, we have an underload, when counting, 2 bundle less 2, 2 bundle less 1, instead of 1 bundle 3, 1 bundle 4. Counting in tens with flexible bundle numbers, we get 38 is 3 bundle 8, which is 2 bundle 18, which is 4 bundle, less 2, or short, with B4 bundle. T is 38, or 3B8, or 2B18, or 4B-2. Likewise with 347. The ancient Danish Vikings said En11, for 11, 1 left. 12, for 12, 2 left. 20t, for 20. Bundle counting fingers in 3s. Counting 10 with overload, normal, or with underload, we get. The total is 2 bundle 4, or 3 bundle 1, or 4 bundle less 2. But, 3 bundles are 1 bundle of bundles. So, a total of 9 is 1 bundle 3s. And 10 is 1 bundle, and 0 bundles, and 1, 3s. Or short, 10 is 101, 3s. So, with units as bundles, and bundle of bundles, we do not need the place value system. Bundle counting in 2s, 4 is bundle, and 8 is bundle. This can be shown with fingers, or with bricks, having different colors. A green 2 brick, is B. A blue 4 brick, is BB. A red 8 brick, is BBB. How to see the unbundled, counted in tens. Counting in tens, a total of 2 tens, and 3 can be described as T equals 2 3, if leaving out the unit, and the decimal point. Or as T equals 2 bundle 3, tens. T equals 3 bundle, less 7, tens. T equals 2, and 3 of 10, bundle, tens. Or, T equals 2.3, tens. T equals 3. Less 7, tens. T equals 2 and 3 of 10, tens. Including the bundle when counting, we get a bundling counting table. So, instead of counting 1, 2, 3, etc. we now count 0 bundle 1, 0 bundle 2, etc., 0 bundle 9, 0 bundle 10, 1 bundle 0. And 9 bundle 8, 9 bundle 9, 9 bundle 10, 10 bundle 0, 1 bundle of bundle, 0 bundle, 0. And 1 bundle of bundle 0 bundle 1, 1 bundle of bundle 0 bundle 2, etc. Flexible bundle numbers ease operations, when using overloads, and underloads. Counting in tens, 74 is 7 bundle 4, which is 6 bundle 14, which is 8 bundle less 6. With addition, 74 plus 18 is 7 bundle 4, plus 1 bundle 8, which is 8 bundle 12, with overload, and 9 bundle 2 without, thus giving 92. Likewise with subtraction, and multiplication. With counting or division, we write 33 bundle 7 with an overload as 28 bundle 56, that counted in sevens gives 4 bundle 8, or 48. So, with overloads and underloads, we don't need to carry or borrow. Children love to make number icons of cars, dolls, spoons, sticks. Changing 4 ones to 1 fours will create a 4 icon with 4 sticks. An icon contains as many sticks as it represents, if written less sloppy. Once created, icons become units when counting in bundles, as children do. Divide and multiply and subtract and add, may be demodeled as icons, also. From 9, push away 4s, we write 9 over 4, iconizing a broom, called division. 2 times lift the 4s to a stack, we write 2 cross 4, iconizing a lift, called multiplication. From 9, pull away 2 4s to find unbundled, we write 9, pull away 2 times 4, iconizing a rope, called subtraction. Uniting next to, or on top, we write B plus C, iconizing the 2 directions, called addition. Calculations predict counting results. Here, we bundle count a total of 9, in twos. 9, bundled in twos, leaves 1 unbundled. We stack the 4 bundles as, 4 times 2. With 1 unbundled placed on top. From 9, 9 over 2 times, we push away 2s. From 9, we pull away 4 2s, leaving 1. So, the calculator prediction is T equals 9 equals 4 bundle 1, 2s. The unbundled is placed on top. Separated by a decimal point, 4.1, 2s, or counted in bundles as 1 equals 1 over 2, times 2, giving 4.5 bundles, 2s, or counting what is missing in a full bundle, 5 bundles less 1, 2s. So, inside decimals, fractions, and negatives, are rooted in, how we outside see the unbundled. Shifting units creates a recount formula. To recount 8 in 2s, division predicts the result, 8 over 2 is 4. So 8 is 4 2s, or 8 is 8, over 2, times 2. So, T is T, over B, times B. This recount formula occurs all over STEM, and it also solves equations. The recount formula solves equations. Asking, how many 2s in 8, gives the equation, U times 2 equals 8. That is solved by recounting 8 in 2s. U times 2 equals 8, but 8 equals 8 over 2 times 2. So, U equals 8 over 2. Thus, solving equations means, moving to opposite side, with opposite calculation sign. This method works all over. Plus to minus, multiplication to division, exponent to root, and base to logarithm. Remember units, when solving equations. In the equation, 2, plus 3 times U, equals 14, we first include the units. 2 times 1, plus 3 times U, equals 14, or 2 plus 3U, equals 14, that splits into, 14 minus 2, plus 2. So, we find U, by recounting 12 in 3s. There is even a hymn for solving equations. Equations are, the best we know. They are solved, by isolation. But first, the bracket must be placed around multiplication. We change the sign, and take away. And only x itself, will stay. We just keep on moving, we never give up. So feed us equations, we don't want to stop. Recounting from icons to tens, asking 6 times 7 is what, we meet algebra, in a bundle square. With no 10 button on a calculator, we cannot use the recount formula. But multiplication gives the result directly, 6 sevens, is 6 times 7, which is 42, which is 4.2, tens, only without units, and without a decimal point. On a pegboard, or a squared paper, we may set up a 10 by 10 square, with 6 and 7 on the sides, written with underloads as bundle less 4, and as bundle less 3. We see that the 6 by 7 block is left when, from the B times B block, we pull away a 3 times B block, and a 4 times B block, and then add, the 4 times 3 block, that was pulled away twice. Again, we see that 6 sevens recounts as, 4 bundle 2, tens. Also we see, that minus times minus must be plus, since it is pulled away twice. Writing the numbers over each other, we see that the result comes from multiplying, first down, then across. Also, we see the FOIL rule, first, outside, inside, and last. Here we recount in tens with overloads, in list, and block, and cross multiplication. In the multiplication list, 16ths are recounted in tens. We see that 8 16ths recounts in 8 bundle 48 tens, that recounts in 12 bundle 8 tens. So, decreasing the base from 16 to 10, will increase the height from 8 to 12.8, to keep the same total. In the multiplication block we see that 34 56s recounts as 190.4 tens. Again, decreasing the base will increase the height, to keep the same total. The same result comes from down and cross multiplication. Increasing a total's base will decrease the height, and vice versa. So a total may be boxed, tenned or squared. A 4x5 box may be squeezed into a 2x10 box, or into a square, with the square root of 20 as sides. We see that the square root of 20 is 4 plus t, since it is between 4 and 5. We also see that the surplus over 16 is 4, which must be shared by the two 4 by t boxes. So, t must be 0.5. So, the square root of 2 is close to 4.5. A calculator shows it is 4.472. Bundle bundles as squares, ease algebra. Placing two playing cards as a square allows solving quadratic equations and studying quadratic rules. With a quadratic equation, u squared plus 6 times u plus 8 as 0, we look at the u plus 3 square. This contains 4 blocks, u squared, 3 times u, twice, and an upper right corner that splits into 8 plus 1. So, in the u plus 3 square, everything disappears but 1, that squares as 1 times 1. The solutions thus are -4, and -2. Placing two A by B cards as an A square, the upper right corner is left, when pulling away 2 cards from the A square, and adding the small b square, that is pulled away twice. And, the t plus b square includes the t square, and the b square, and 2t by b block. Recounting in 2 units creates pair numbers and proportionality. Recounting in kilogram and dollar, we get a pair number 4 kilograms per $5, or 4 per 5 kilogram per dollar. With like units, pair numbers become fractions. $4 per $5 is 4 per 5, and $4 per $100 is 4 per 100, or 4%. With 4 kilograms linked to $5, we simply recount in the pair number, when asking, 12 kilograms is how many $? 12 kilograms is 12 over 4 times 4 kilograms, which is 12 over 4 times $5, which is $15. However, proportionality questions may also be answered in many other ways. Proportionality shows the flexibility of the unit math paradigm. Proportionality typically has 2 questions. Q1, 2 kg costs $5, what does 7 kilograms cost? And Q2, what does $12 buy? 1. Regular, detri, rule of 3, used in the Italian Renaissance. Rephrase with shifting units, the unknown at last. From behind, first multiply, then divide. Q1, 2 kg cost $5, 7 kilograms cost how many $? First multiply, then divide gives the dollar number, 7 times 5, over 2, equals 17.5. 2. Find the unit. Q1, 1 kg costs 5 over 2, so 7 kilograms cost 7 times 5, over 2, equals $17.5. 3. Cross multiplication. Q1, 2 over 5, equals 7 over u, so 2 times u, equals 7 times 5, so u equals 7 times 5, over 2, equals 17.5. 4. Recounting in the pair number, 2 kilograms per $5, coming from recounting the total t, in both kilogram and dollar. Q1, t equals 7 kilograms, equals 7 over 2, times 2, kilogram, equals 7 over 2, times $5, equals $17.5. Proportionality also shows the inflexibility of greenhouse mathematics. Without units, you must set up a so-called model, with linear functions, using group theory, from abstract algebra. We choose a linear function, f of x, equals c times x, from the set of positive kilogram numbers, to the set of positive dollar numbers. So, it has the real numbers, as its domain. Knowing that f of 2, that is c times 2, has the value 5, this equation is solved by multiplying with the inverse element to 2 on both sides, and by applying the associative law, and the definition of an inverse element, and of the neutral element under multiplication. In the end, this gives c equals 5 over 2. With f of x equals 5 over 2, times x, the inverse function is f, negative 1, of x, equals 2 over 5, times x. With 7 kilograms, the answer is f of 7 equals 5 over 2, times 7, equals $17.5. With $12, the answer is f, negative 1, of 12, equals 2 over 5, times 12, equals 4.8 kilograms. Recounting gives pair numbers, in STEM multiplication formulas. STEM typically contains multiplication formulas, with pair numbers coming from recounting. Examples. Kilogram, equals, kilogram per cubic meter, times cubic meter, equals density, times cubic meter. Meter, equals, meter per second, times second, equals speed, times second. Energy, equals, energy per second, times second, equals watt, times second. Extra examples from STEM, and from economics. With like units, pair numbers become fractions, both operators, needing numbers, to become numbers. In a box with 2 red per 3 apples, recounting reds and apples gives the fraction 2 per 3, reds per apples. How many red apples are there among 12 apples? To predict the result, we recount 12 apples, in the pair number, 3 apples. T equals 12 apples, equals, 12 over 3, times 3 apples. Which gives, 12 over 3, times 2 red, equals 8 red apples. Or, we equal the pair numbers. U over 12, equals 2 over 3, so U equals 2 over 3, times 12, equals 8. Here, we move 12 to opposite side, with opposite calculation sign. Enlarging, or shortening fractions. Taking 2 of 3 from 12, means taking 2 per 3, of 12. With 2 bridged to 3, we recount 12 in threes, 12, equals, 12 over 3, times 3, equals 4 times 3, equals 4 threes. So, 4 times we can take 2, that is 8, from the 12. Thus 2 per 3, equals 8 per 12. This may be used for enlarging, or shortening, fractions, by inserting, or removing, the same unit, above and below the fraction line. 2 over 3, equals 2 fours, over 3 fours, equals 2 times 4, over 3 times 4, equals 8 over 12, and vice versa. Recounting the sides in a block, halved by its diagonal, gives trigonometry, and pi. A block cut by its diagonal creates a right triangle with 3 sides. The base B, the height h, and the cut c. They connect with the angle A, by pair number formulas, recounting the sides pairwise. H is, h over b, times b, which is tangent angle, times b. H times h, plus b times b, is c times c, so the diagonal adds bundles. A circle contains very many small half blocks. This provides a tangent formula for the number pi. The tangent angle is the change of y, over the change of x, which is the diagonal gradient. Switching, uniting, and splitting units. Turning a 2D block, will change the unit. T, equals 2 threes, equals 2 times 3, becomes T, equals 3 twos, equals 3 times 2. So, T, equals 2 times 3, equals 3 times 2, the commutative law. Turning a 3D block, will also change the unit. So, T equals 2 times 3, equals, 2 times 2, times 3, the associative law. A block may split into 2 parts. T, equals 3 fives, equals 3 twos, plus 3 threes. So, T, equals 3 times 5, equals 3 times 2 plus 3, equals 3 times 2, plus 3 times 3, the distributive law. Prime numbers, and foldable numbers. When can blocks be folded, in like bundles? The block T, equals 2 fours, equals 2 times 4, has 4 as the bundle unit. Turning it over gives T, equals 4 twos, equals 4 times 2, now with 2 as the bundle unit. So, 4s can be folded in another bundle unit, as 2 2s, whereas 2s cannot. 1 is not a bundle, nor a unit, since a bundle of bundles stays as 1. We call 2 a prime unit number, and 4 a foldable unit number. 4 equals 2 2s. A block of 3 2s cannot be folded in like bundles. A block of 3 4s can be folded. T equals 3 4s equals 3 times 2 times 2 equals 3 times 2 times 2 equals 2, 3 times 2s. A number is called even if it can be written with 2 as the unit, else the number is called odd. Finding possible units. What are the possible units, in a total of 12? Units come from folding, in prime units. T equals 12 equals 2 times 2 times 3. So, 1 12s may be reshaped into 2 6s, or into 3 4s, or into 4 3s, or into 6 2s. Recounting large numbers in, or from, tens, gives the same size, but a new form. Recounting 6 47s, in tens. T equals 6 47s, equals 6 times 47, equals 6 times 4 bundle 7, equals 28 bundle 2, equals 28.2 tens. Recounting 476, in sevens. T equals 476, equals 47.6 tens, equals 47 bundle 6, equals 42 bundle 56, equals 6 times 7, bundle, 8 times 7, equals 68 times 7 equals 68 sevens. Operators become areas, before adding. Digits are operators, needing a number, to become a number. And, paranumbers and fractions are also operators. So, to add, operators must first be multiplied, to become a number. But multiplying creates areas. Digits, and paranumbers, and fractions, thus add as areas, that is, as integral calculus. So, calculus comes in 3 versions. Primary school calculus. Adding digits, as bundle number blocks. Middle school calculus. Adding constant paranumbers, and constant fractions. High school calculus. Adding changing paranumbers. In unit math, blocks are fundamental. Children see many as blocks, with a number of bundles, and use flexible bundle numbers with units, and with overloads, or underloads. In numbers, 456 is 3 blocks. In algebra, blocks add next to, or on top. In geometry, trigonometry comes, when recounting half blocks. Once counted and recounted, totals may be added, but next to, or on top. Adding 4 5s and 2 3s next to as 8s, means adding areas, as in integral calculus. Adding them on top as 5s, means changing units, by recounting. Reversing next to addition. If T1 as 2 3s, together with T2 add next to, as 4 7s, then what is T2? We pull away the initial block, T1, before recounting the rest in 4s. The recount formula predicts the result. So, we pull away the 2 3s from the 4 7s, before recounting in 4s. Since reversed next to addition finds area differences, it is called differential calculus. Here subtraction precedes division, which is natural as reversed integration. Paranumbers add as areas, called integral calculus. We ask, 2 kilograms at $3 per kilogram, plus 4 kilograms at $5 per kilogram, is 6 kilograms at how many $ per kilogram? We see, that unit numbers add directly. But, that paranumbers must be multiplied to unit numbers, to be added. And, since multiplication creates areas, paranumbers add as areas, under the paranumber curve. So, in integration, multiplication comes before addition. Therefore, paranumbers and fractions are not numbers, but operators, needing numbers to become numbers. Here, the paranumber curve is piecewise constant. It becomes locally constant by interchanging epsilon and delta. Then the sums are replaced, by integrals. Subtracting paranumbers is called differentiation. Reversing adding paranumbers, we ask. 2 kilograms at $3 per kilogram, plus 4 kilograms at what, gives, 6 kilograms at $5 per kilogram. We first pull away the initial 2 by 3 block, before we recount the rest, in 4s, to get the paranumber. So, reversed paranumber addition means subtracting areas, to be reshaped, called differential calculus. Here subtraction, giving a change, delta, comes before division, the reverse of multiplication before addition, in integral calculus. Adding fractions without units creates a fraction paradox. The teacher asks, what is 1 over 2, plus 2 over 3? The students answer, well, 1 over 2, plus 2 over 3, equals 1 plus 2, over 2 plus 3, which is 3 over 5. No, that is wrong. 1 over 2, plus 2 over 3, equals 3 over 6, plus 4 over 6, equals 7 over 6. But, 1 red of 2 apples, plus 2 red of 3 apples, is 1 plus 2 red, of 2 plus 3 apples, that is, 3 red, of 5 apples. How can it be 7 red, out of 6 apples? Inside this classroom, 1 over 2, plus 2 over 3, is 7 over 6, always. Again we see, that fractions are not numbers, but operators, needing numbers, to become numbers. Adding operators without units, often fails outside the no-unit math greenhouse. Mixing English and metric units, made NASA's Mars Climate Orbiter fail, in 1999. Adding numbers with like units, 6 plus 9. Inside the no-unit math paradigm, numbers add serial, or next to, on the number line. We find the result by counting on from 6, or from 9. Outside, in the unit math paradigm, numbers add parallel, or on top, showing that 6 plus 9 is 2 bundle 3 6s, or 2 bundle less 3 9s, or 2 bundle less 5 10s, or 1 bundle 5 10s, or 15. Added directly as less numbers. 6 plus 9 is bundle less 4, plus bundle less 1, which is 2 bundle less 5, which is 15. Subtracting numbers with like units, 9 minus 6. Inside the no-unit math paradigm, numbers subtract serial, or next to, on the number line. We find the result by counting backwards. Outside, in the unit math paradigm, numbers subtract parallel, or on top, showing that t is 9 minus 6, which is 3, or that t is 6 minus 9, which is less 3, since 6 is 9 less 3. Subtracting directly as less numbers, gives the same result. Again we see, that minus minus, is plus. Adding, or subtracting, unspecified numbers. Only add like units, so how to add a total, of 4 times a, times b squared, plus 6 times a, times b, times c. With 2 times 3 as 2 3s, here units come from folding, or factoring. T equals 4 times a, times b squared, plus 6 times a, times b, times c. Equals 2 times 2, times a, times b, plus 2 times 3, times a, times b, times c. Equals 2 times b, times 2, times a, times b, plus 3 times c, times 2, times a, times b. Equals 2b plus 3c, times 2ab. Equals 2b plus 3c, with the common unit, 2ab. We might want to use a factor filter, to find the common unit. Change by adding, and by multiplying. Change by adding, gives a linear change formula. Adding $3 per day, to $2, gives a total of 2, plus 3 times n, after n days. The general formula is also called, change by adding. Change by multiplying, gives an exponential change formula. Adding 3% per day to $2, gives a total of 2, times 103% power n, after n days, since adding 3%, means multiplying with 103%. The general formula is also called, change by multiplying. Combining the two gives a simple saving formula, capital A over minor a is, capital R over minor r, where minor a, and minor r, are the per day dollar, and percent input, and where capital A, and capital R are the final dollar, and percent output, and where 1 plus capital R, is 1 plus minor r, power n. In an installment plan, a saving races against a debt formula, D is due, times, 1 plus r, power n. Splitting up 100% in n pieces, gives the Euler number, E. E is 1 plus 1 over n, power n, for n large. Reversing change by adding, and by multiplying. Reversing change by adding, gives one equation. 100 is 20, plus 5 times u, easily solved by splitting, and recounting. 100 is 100 minus 20, plus 20, so u times 5 is 100, minus 20, which is 80. But 80 is 80 over 5, times 5, so u is 80, over 5, which is 16. Reversing change by multiplying, gives two equations. In 20 is u power 5, 5 factors u give 20, predicted by a factor finding root. U is the fifth root of 20, which a calculator finds as 1.82. In 20 is 5 power u, u factors 5 give 20, predicted by a factor counting logarithm, u is log 5 of 20, which a calculator finds as 1.86. There are 4 ways to unite, or to split a total. A number formula t equals 345 equals 3 bundle 4 bundle 5 is called a polynomial. It shows the 4 ways to unite: addition, multiplication, power, and next to block addition, also called integration. Addition and multiplication unite changing and constant unit numbers. Integration and power unite changing and constant pair numbers. We might call this beautiful simplicity the algebra square, since in Arabic, algebra means to reunite. The 4 uniting operations each has a reverse splitting operation. Addition has subtraction, and multiplication has division. Power has the factor finding root, and the factor counting logarithm. Integration has pair number finding, also called differentiation. Reversing operations means solving equations, done by moving to opposite side, with opposite calculation sign. There are 8 competencies, inside the no-unit greenhouse, but only 2 competencies, outside the greenhouse. To master many, first you bundle count, and recount, then you add. OECD expresses its view on competencies, in its learning framework, 2030. Instead of mathematics, it points to numeracy. Concepts have different definitions inside the no-unit math, and outside, in the unit math paradigm. The goal of mathematics education. Inside, it is to master, first mathematics, later many. Outside, it is to master, first many, later mathematics. The basis of mathematics. Inside, it is sets, expressions, and functions. Outside, it is many, counted and added, and reported in full sentences. What kind of science is mathematics? Inside, it is a pure science. Outside, it is a natural science, about many. Self-reference. Inside, it is meaningful. Outside, it is meaningless. Validity. Inside, addition and multiplication are both always valid. Outside, multiplication is always valid, addition is only sometimes valid. Education. Inside, it is mediating institutionalized essence. Outside, it is exploring existing subjects. Theorist. Inside, it is Vygotsky. Outside, it is Piaget. Competence. Inside, 8 is needed to master math. Outside, 2 is needed to master many, count and add. Accessible. Inside, it is only to few. Outside, it is to all. Models. Inside, all are fiction. Outside, there is fact and fiction as in the word language. Digits. Inside, they are symbols, as letters. Outside, they are icons, with as many sticks, as they represent. Many digits. Inside, it is one number, obeying a place value system. Outside, it is many numbers, numbering and bundled, bundles, bundle of bundles, etc. Numbers. Inside, it is line numbers with lengths, without units. Outside, it is block numbers with areas, and with units. Types. Inside, it is cardinal and ordinal numbers. Outside, it is space and time numbers. Divide, 8 over 2. Inside, it is equal sharing, 8 equally shared by 2. Outside, it is bundle counting, 8 counted in twos. Multiply, 6 times 7. Inside, it is 6 times 7 equals 42 equals 4.2 tens, recounted in tens. Outside, it is 6 times 7 equals 6 sevens, a block that may, or may not recount in tens. Subtract, 7 minus 2. Inside, it is take away singles, 7 minus 2 equals 5. Outside, it is pull away a block to look for unbundled singles, 7 minus 2 times 3 equals 1. So, t equals 7 equals 2 bundle 1, 3s. Add. Inside, it is uniting line segments, 2 plus 3 equals 5. Outside, it is uniting areas on top, or next to, also called integral calculus. 2 3s plus 4 5s equals how many 5s, or 2 3s plus 4 5s equals how many 8s. Pair number. Inside, it is not recognized. Outside, it is recounting, in 2 units. Fraction. Inside, it is a rational number, to add without units. Outside, it is a pair number, and both are operators, needing a number to become a number, so they add, by areas, as integral calculus. Geometry. Inside, it is plane, coordinate, and trigonometry last. Outside, it is trigonometry, coordinate, and plane last. Equations. Inside, it is equivalence relations, solved by using abstract algebraic, group theory. Outside, it is reverse calculations, solved by moving to opposite side, with opposite calculation sign. Function. Inside, it is a subset, of a set product, where first component identity, implies second component identity. Outside, it is a number language sentence, or formula, with a subject, and a predicate. Graph. Inside, it is a subset, in a set product. Outside, it is running numbers, in a plane. Linear function. Inside, it is a homomorphism. Outside, it is a function with constant change pair number, or gradient, or slope. Differentiable. Inside, it is a smooth function, meeting an epsilon delta condition. Outside, it is a locally linear function, with a locally constant change per number, dy over dx. Continuous. Inside, it is a function, meeting an epsilon delta condition. Outside, it is a locally constant function, as a piecewise constant function, only epsilon and delta change places. Root, logarithm. Inside, they are irrational numbers. Outside, root is a factor finder, and log is a factor counter. Precalculus. Inside, it is linear, and exponential functions. Outside, it is constant change, by adding, and by multiplying. Statistics. Inside, it is stochastics, and random variables. Outside, it is unpredictable change, predicted by a mean, and a median. Quadratics. Inside, it is degree 2 polynomials, to factorize. Outside, it is constant changing change, and curvature. Calculus. Inside, it is derivatives, and antiderivatives. Outside, it is adding locally constant pair numbers, and finding them. Differential. Inside, it is derivatives as limits, first. Outside, it is change, predicted by locally constant pair numbers, next. Integral. Finding antiderivatives, next. Outside, it is adding locally constant pair numbers, by areas, first. Differential equations. Inside, only few have solutions, and numerical methods should be avoided. Outside, it is change formulas, numerically solved by a computer, adding its changes, to a total change. Vectors. Inside, a vector space is the top algebraic structure. Outside, it is a quick way, to do 2D and 3D, coordinate geometry. Solving equations by recounting, we may bracket group theory, from abstract algebra. Outside the no-unit math paradigm, we solve the equation, 2 times u is 8, by recounting 8 in 2s. 8 is 8, over 2, times 2, so u is 8 over 2. Found by moving to opposite side, with opposite calculation sign. Finally, we test to see, if 4 is the number, that multiplied with 2 gives 8. Inside the no-unit math paradigm, we do not test, but we must remember the by implication arrows. First we observe, that multiplication has 1, as its neutral element, and that 2 has a half, as its inverse element. Then comes multiplying the inverse element to 2, that is, a half, to both number names. Then comes applying the commutative law to u times 2. And using 4 as the short number name for 8 times a half. Then comes applying the associative law. Then comes applying the definition, of an inverse element. Then comes applying the definition, of a neutral element. Again, with arrows, a test is not needed. We now can show the solution set for the child's own unit math curriculum. Digits are sloppy icons with as many sticks as they represent. Totals are counted by bundling, giving geometrical multi-blocks and algebraic bundle numbers with units when the blocks are turned to hide the units behind. Operations are icons also, showing the 3 counting steps. First we push and lift bundles. Then we pull away stacks to find the unbundled ones. The operation order is division first, then multiplication, then subtraction. Addition next to, and on top, comes later, after totals are counted and recounted. Counting and recounting is big fun when predicted by a calculator with the recount formula: T is T over B times B. Or, the total T contains T over B times B. Question: T equals 4 5s, equals how many 3s? Answer: T equals 4 5s, equals 6 bundle 2, 3s, as predicted by a calculator. Differences to the no-unit math curriculum. A no-unit math curriculum operates on specified and unspecified numbers. Digits are given directly as symbols, without letting children discover digits as icons, with as many strokes or sticks as they represent. Numbers are one-dimensional line numbers, with digits respecting a place value system. Without letting children discover the thrill of two-dimensional bundling and stacking, counting both singles and bundles of bundles, etc., and also including the units. Seldom, if ever, 0 is included in the counting sequence as 0 bundle 1, 0 bundle 2, 0 bundle 3. In order to show the importance of bundles as units. Never children are told that 11 and 12 comes from the Vikings, counting 10 and 1 left, and 10 and 2 left. Never children use full number language sentences, T equals 2 5s, including both a subject and a verb, and a predicate with a unit. Seldom children are asked to describe numbers after 10 as 1 bundle 4 10s, or 1 10 4, or 1.4 10s, with a unit, and with a decimal point to separate bundles and unbundled singles. Seldom 17 is recounted as 2 bundle, less 3 10s, or 2.3 10s. Nor is 24 recounted as 1 bundle 14 10s, or 3 bundle less 6 10s. The tradition never respects the natural order of operations. Instead, it turns the order around, by giving addition without units priority over subtraction, and multiplication, and division. In short, children never experience the enchantment of counting and recounting many, before being forced to add on top only, thus neglecting next to addition. Re-enchanting many therefore is a goal for the unit math curriculum, in mastery of many. So, it respects and develops the children's existing mastery of many, by counting before adding, and by using flexible bundle numbers, with units. Summary: what is the core difference between no-unit math and unit math? Digits, as 4. 4 is a symbol, as letters. No, 4 is an icon with 4 strokes. Numbers, as 456. It is one number. No, it is 3 numberings, 4 bundle of bundles, and 5 bundles, and 6 unbundled ones. Division, as 8 over 2. It means 8 split in 2. No, it means 8 counted in twos. Multiplication, as 6 times 7. It gives 42. No, it is 6 sevens, that may, or may not, be recounted as 4 bundle 2 10s. Addition, as 2 plus 3. 2 plus 3 is 5 always. No, it depends on the units, and on, if the totals are added next to, or on top. 2 4s plus 3 5s, equals 2 bundled 3 9s, if added next to. And, 4 bundle 1 5s, if added on top. Equations, as 3 times u, equals 12. We neutralize stepwise, using group theory, from abstract algebra. No, we recount, or simply move the known, to opposite side, with opposite calculation sign. Fractions, as 2 over 3. It is a number, and 1 over 2, plus 2 over 3, is 7 over 6, always. No, it is a pair number. Both are not numbers, but operators, needing numbers, to become numbers. And 1 over 2, plus 2 over 3, is 3 over 5, with 2 and 3 apples. So, there are different answers from essence-based and existence-based mathematics education. In philosophy, the answers are 1. Line numbers. No. Area numbers, that is, flexible bundle numbers, with units. 2. Addition first, division last. No. Division first, addition last, push, lift, pull, add. 3. Fractions are numbers. No. Fractions are numbers, that is, not numbers, but operators, needing numbers to become numbers. 4. Geometry before trigonometry. No. Trigonometry before geometry. 5. Late calculus, and differentiation before integration. No. Primary, middle and high school calculus. And integration before differentiation. And, in sociology, the answers are 1. Serve institutional knowledge. No. Facilitate individual knowledge construction. 2. Use thick textbooks. No. Use short compendia with models. 3. Accept goal displacement. Mastery of mathematics is the goal. Later, others may apply mathematics. No. Reject goal displacement. Mastery of many is the goal. Later, mastery of essence-based mathematics may be tried, if needed. And, in psychology, the answers are 1. Mediate knowledge about expressions. No. Communicate about many, in full sentences, with an outside subject, and an inside chosen predicate. 2. High dropout rate accepted, and explained by theory-based research. No. Low dropout rate with grounded design research. Conclusion. The outside, unit math paradigm, provides the same mathematics, as the inside, no unit math paradigm, only in a different order. And, the unit math paradigm, avoids the inside paradigm's mathema-tism, with its falsifiable, addition claims. So, to become a full science, mathematics should leave its 1 plus 2 is 3, no unit math greenhouse, and accept that, of course, numbers cannot add, without units. It should teach the outside counting before adding, unit math, paradigm. Where numbers and operations are icons, linked directly to existing things, and actions. Where totals are bundle counted, to create flexible bundle numbers, that with overloads and underloads include decimals, negatives, and fractions, for the unbundled singles. Where recounting to change the unit, creates a recount formula, T is T, over B, times B, that solves proportionality equations, all over mathematics, and STEM. And, where adding next to, and on top, leads directly to the math core, calculus, and linearity. Bundle counting means pushing away bundles by division, lifting bundles into a block by multiplication, and pulling away the block to find unbundled singles, that may be counted as decimals, fractions or negatives. Recounting a total in another unit creates a recount formula, T is, T over B, times B, predicting recounting results and proportionality all over STEM. Recounting from tens to icons gives multiplication equations solved by moving known numbers to opposite side with opposite calculation sign. Recounting from icons to tens roots multiplication tables, and algebra. Recounting in physical units creates pair numbers, becoming fractions with like units, both are not numbers, but operators needing numbers to become numbers. Recounting the sides in a block halved by its diagonal creates trigonometry and pi. Adding blocks next to means integrating areas, thus becoming integral calculus. Subtracting blocks, then becomes differential calculus. Adding blocks on top, the units become like, through proportional recounting. Pair numbers add by their areas, under the pair number graph. A total may change by adding, or by multiplying. Reversing change by multiplying, gives the factor finding root, and the factor counting logarithm. The algebra square shows the 4 ways, to unite parts into a total, and the 5 ways, to split a total into parts. In philosophy, the unit math paradigm resonates with existentialism, where existence precedes essence, and with Piaget psychology, where learning takes place through guided meetings, with the subjects. And not by having institutionalized essence mediated. The communicative turn, in language education. Before 1970, foreign language was taught as an example of its grammar. Then a reaction came, with the communicative turn. Halliday said, a functional approach to language means investigating how language is used, trying to find out what are the purposes that language serves for us. Likewise, Widow-Sun adopts a communicative approach to the teaching of language, allowing more students to learn a language through its use for communication about outside things and actions. So, the question is, can mathematics also have its communicative turn? A final question. In the United Nations 17 Sustainable Development Goals, number 4 is about quality education. Should ethical quality education force children to enter inside a no-unit math greenhouse that slowly strangles their innate number language by using line numbers to learn no-unit addition that folds outside? Where children's innate mastery of many just waits to be developed by flexible bundle numbers available at their fingertips. Bundle count before you add booklet. Free to download. The free booklet is called Math Dislike, Cured by Flexible Bundle Numbers. My many math tears will not stay if I bundle the stray away. The booklet shows how 5 sticks can be counted in twos, in 3 different ways. With an overload, as 1 bundle 3 twos. Normal, as 2 bundle 1 twos. And with an underload, as 3 bundle less 1 twos. The booklet contains a chapter with examples. And 20 chapters, with exercises in flexible bundle counting. Enjoy. 1-day free Zoom seminar. To cure math dislike, bundle count, before you add. Action learning, based on the child's own flexible bundle numbers, with units. 9 to 11. Listen and discuss the PowerPoint presentation. Flexible bundle numbers develops children's innate mastery of many. From mathema-tism to menomath. Mathema-tism combines mathematics and mathematism. Mathematics presents a concept, top-down, as an example, instead of bottom-up, as an abstraction. Mathematism is true inside, but seldom outside, the no-unit math greenhouse. Menomath is a natural science about many, mastering many by bundle counting, recounting, and adding next to, and on top. 11 to 13. Zoom conference, and lunch. 13 to 15. Workshop in the Bundle Count Before You Add booklet, to experience proportionality, and calculus, and solving equations, as golden learning opportunities, in bundle counting, and next to addition. 15 to 16. Coffee, and Zoom conference. 8 microcurricula for action learning, and research. C1. Create icons. C2. Count in icons. C3. Recount in the same icon, negative numbers. C4. Recount in a different icon, proportionality. A1. Add on top, proportionality. A2. Add next to, integrate. A3. Reverse adding on top, solve equations. A4. Reverse adding next to, differentiate. Question guided, teacher education. mathecademy.net. Teaches teachers to teach mathematics, as menomath, a natural science, about many. To learn math, count, and add many, using the CATS method. Count and add, in time and space. Primary school. C1, and A1, and T1, and S1. Secondary school. C2, and A2, and T2, and S2. mathecademy.net, a virus academy. Ask many, not the instructor. Teacher training in menomath, using CATS, count and add, in time and space. Question guided, teacher education. An example from C1, counting in primary school. Question. How to count many? Answer. By bundling and stacking the total, T, predicted by the recount formula, T is, T over B, times B. Question. How to recount 7 in threes? T equals 7, equals how many threes? Answer. T equals 7 equals, 7 over 3, times 3, equals 2 bundle 1, threes, equals 2.1 threes, equals 2 and 1 over 3, threes, equals 3 bundle less 1, threes. Question. How to recount 6 kilograms in dollar? T equals 6 kilograms equals how many dollar? Answer. Recount in the pair number, 4 kilograms per $2. So, 6 kilograms, equals, 6 over 4, times 4, kilogram, equals 6 over 4, times $2, equals $3. Question. How to count in standard bundles? Answer. Bundling bundles, gives a multistack, a polynomial. T equals 423, equals 4 10 10, 2 10, 3, equals 4 bundle bundle, 2 bundle, 3, equals 4 times bundle squared, plus 2 times bundle, plus 3. Pyramid education. In pyramid education, a group of 8 teachers are organized in 2 teams of 4, choosing 2 instructors, and 3 pairs, by turn. Each pair works together to solve count and add problems. The coach assists the instructors when instructing their team, and when correcting their count and add assignments. Each teacher pays by coaching a new group of 8 teachers. You may want to watch some Mr. L. Tup YouTube videos. Here are some examples. Postmodern mathematics debate. Recounting removes math dislike. Icon counting and next-to addition. Preschool mathematics. Fractions. Pre-calculus. Calculus. Mandarin mathematics. World history. Difference research finds differences that makes a difference. By using action learning or action research. Uncover a difference by asking, is this so, by nature or by choice? Design a microcurriculum, including the difference. Test the microcurriculum. Observe what difference the difference makes. Share your observations with local peers. Listen to their comments, and then redesign the microcurriculum. After 2 to 3 cycles of redesigning, testing, observing, sharing, and listening, it is time to publish your work to global peers, at conferences. And to send it to an educational journal, as an example of action learning. Or to a research journal, as an example of action research. Recounting looks like Dean's multi-base blocks. Dean's name is synonymous with the multi-base blocks, also known as Dean's blocks, which he invented for the teaching of place value. He also is the inventor of algebraic materials, and logic blocks, which sowed the seeds of contemporary uses of manipulative materials in mathematics instruction. Dean's place is unique in the field of mathematics education, because of his theories on how mathematical structures can be taught from the early grades onwards, using multiple embodiments through manipulatives, games, stories, and dance. Dean's on numbers, and multi-base blocks. The position of the written digits in a written number tells us whether they are counting singles or tens or hundreds or higher powers. This is why our system of numbering, introduced in the Middle Ages by Arabs, is called the place value system. My contention has been that in order to fully understand how the system works, we have to understand the concept of power. In school, when young children learn how to write numbers, they use the base 10 exclusively and they only use the exponents 0 and 1, namely denoting units and tens, since for some time they do not go beyond 2-digit numbers. So neither the base nor the exponent are varied, and it is a small wonder that children have trouble in understanding the place value convention. Educators today use the multibase blocks, but most of them only use the base 10, yet they call the set multibase. These educators miss the point of the material entirely. Unit math turns meta math upside down. Dean's teaches the one-dimensional place value system with 2-dimensional and 3-dimensional blocks, to illustrate the importance of the power concept. Unit math teaches decimal numbers with units, and stays with 2-dimensional blocks, to illustrate the importance of bundle units, and of adding areas. Dean's wants to bring examples of abstractions to the classroom. Unit math wants to build abstractions from concrete examples, brought to the classroom. Dean's teaches top-down meta-math, derived from the concept, set. Unit math is a bottom-up natural science, about the physical fact many, and sees set as a meaningless concept, because of Russell's set paradox, saying that the set of sets, not belonging to itself, belongs to itself, if it does not. The theoretical background for this presentation is 3 articles. Mastering Many, by counting and recounting, before adding, on top and next to. Demodeling numbers, operations, and equations. From inside to outside, understanding. And, bundles bring back brains, from unethical special education. This presentation, and its PDF, may be found here, at the mathacademy.net website. Questions and answers, are shown here also. Mail, alan.tup@mathacademy.net. YouTube channel, Mr. Al. Tup.